Hi, my name is Tom Hoeffel, and this channel is all about helping students learn chemistry. In today's video, we're going to be talking about valence shell electron pair repulsion theory. So by the end of this video, if you pay attention real closely, you'll be able to identify the geometry of a lot of different molecules from 2 domains all the way up to 6 domains. So let's get right into it. Let's talk about what an electron domain is to begin with. So a good definition for electron domain is an area that is dense in electrons. Okay, so an area that is dense in electrons is what we call an electron domain. And to be able to do the geometry of molecules, you got to be able to look at an atom and center in on the central atom and decide how many electron domains are around it. So what counts as an electron domain? A single, double, or triple bond, they all count as one domain. So one of the things that students get a little confused with is that they understand that a single bond would be an electron domain, but sometimes they think a double bond is 2 domains and a triple bond is 3 domains, and that's not true. Okay, all of these things count as one electron domain. Okay, of course, the lone pair will also count as an electron domain as well. So being able to count the number of electron domains around the central atom is the imperative part before you determine the geometry of that particular molecule. So let's do some practice on counting the number of electron domains around a central atom. So right here I have a water molecule, and when we do geometry, remember we're always focusing in on the central atom. And central atom in this problem is going to be the oxygen. Okay, we got a bonding domain here, a bonding domain here, a lone pair here, and a lone pair here. So this water molecule has 4 total domains. 2 of them are bonding and 2 of them are non-bonding. And understanding which ones are bonding and which ones are non-bonding, that too will end up being important when we're determining the geometry. So this thing has a total of 4 electron domains, 2 bonding, 2 non-bonding. Now let's take a look at carbon dioxide. Okay, this is another molecule that's drawn. And when we investigate the central atom, we see a double bond on the left-hand side and a double bond on the right-hand side. Now, I want to remind you that an electron domain is an area that's dense in electrons. So this area is dense in electrons. This double bond, though, only counts as 1 electron domain. And then this double bond will count as 1 electron domain. So around the carbon, there are no lone pairs. There's just this double bond that's an electron domain and this double bond, which is an electron domain, for a total of 2 electron domains. This area and this area. So I'm hoping you guys start to understand how to count these electron domains. Then we move over to these 2 structures. Now, these are actual molecules. Over here, what we have is something called AB format, where the A could represent any element as long as the A is the central atom, and then the B is what we'd call non-central atoms. So like kind of like the hydrogens would be the B's over here, if you will. Okay. At any rate, okay, even in AB format, we should be able to count the number of electron domains. If I go around the central atom, I see a bonding domain here, a bonding domain here, a bonding domain here, no lone pairs. So this guy has a total of 3 electron domains around its central atom. Okay, and that's going to lead to a particular shape for that particular structure. And then the last one, we're going to take a look at it. We got a bonding domain here, a bonding domain here, and then there's a couple lone pairs. There's a lone pair here and a lone pair here. So this structure has a total of 4 electron domains. And really, this AB format could be representing something like water. Okay. Now remember, the number of electron domains will end up determining the overall geometry. Okay, so now that we can count electron domains, let's go ahead and get into the geometry of these different structures. Okay, so we're going to start out with 2 electron domains, and then we're going to work our way up to a structure that might have 6 electron domains. So if you stick with this to the very end, you're going to be able to do geometry for all of these different types of molecular compounds. And when I use the word molecular, it really just means these covalent compounds. Okay. So one of the things that we're going to have to do is we're going to talk about the electron domain geometry, which I'm going to abbreviate as EDG. And what electron domain geometry is, it's going to be the shape that the electrons make. So in parentheses, I'm just putting electrons over there. And then we're going to have something that's called molecular geometry. And molecular geometry is going to be the shape that the atoms make. So in parentheses over here, I'm going to write down the word atoms to remind you that molecular geometry is the shape of the atoms, and electron domain geometry is going to be the shape of the electrons. And then lastly, we're going to have something labeled as BA, which stands for the bond angle. All right, so let's get into it. Okay, I'm going to be using these water bottles to describe electron domains. So this water bottle, it could be a single bond, a double bond, a triple bond, or even a lone pair. We just know that's an area that's really dense in electrons. And if I have two electron domains, based on valence shell electron pair repulsion theory, they would never ever line up like this. Okay, they're going to repel as much as they possibly can. Okay, so where my hand is right now is what we'd call the central atom A. And if each of these are bonding domains, then there will be an element B right here where my fist is right here, and an element B right here because they represent non-central atoms. But to maximize the repulsion, this is the shape that I would get, okay? And I'm just going to draw this on the board in that AB format. Okay, so what I just showed you would be something that would look like this, where A has two electron domains and they get as far apart from each other as possible. Now you might be able to figure this out logically, that the bond angle here would be 180 degrees. Remember, a whole circle is 360, so half would be 180 and then the other half would be another 180. So the bond angle here is going to be 180 degrees. Okay. Now the electron shape, okay, remember, is just the domains, and it looks like it's going to be a straight line. And we're going to use a fancy word for straight line as linear. So a big part of this video is understanding the vocabulary word that describes the shape of the electrons and the vocabulary word that describes the shape of the atoms. Okay. Now, if the electrons are making this linear shape and there's atoms on the other side, well, if everything's bonding, then the electron domain geometry and the molecular geometry is going to be the same. I still have this straight line, so the molecular geometry is going to be linear as well. Okay, so if you have everything that makes a straight line, if the electrons make a straight line, the electron domain geometry is linear, and if the atoms kind of go in a straight line, we're going to say the molecular geometry is linear as well. Okay, so that kind of explains two domains. Okay, well, I have a question for you. Okay, if we have two domains, okay, and we want to introduce a third domain, what would happen? Okay, well, if I bring in a third domain right here, these two electron domains are not going to stay put. Okay, they're going to be repelled by these electrons. And maybe you can already think of the shape that's going to happen. But when this comes in, I think these are going to be like kind of like pushed down until they maximize their angles. Now I have a model that shows that, so I can hold it with one hand. Okay, it would make something that looks like this. Okay, so we got this domain, this domain, this domain. This is a total of 3 electron domains, and I can't push these any further away. If I push this one down further, it'd get closer to this water bottle. If I push that one up, it'd get closer to this water bottle. This angle is maximizing the space between these 3 electron domains. They can't get any further than what they already are right now. Okay, so this angle is going to be 120, this is going to be 120, and this is going to be 120 for a total of 360 degrees all the way around. Okay, so I'm going to put this down, and I'm going to draw that shape on the board. I'm going to erase all of this because we got new geometry, because now we're talking about 3 domains instead of 2. And if I was to draw this picture in the AB format on the board, I would get something that would look like this, where I would have 120 degrees here, 120 degrees here, and 120 degrees here. So we'd say that this is 120 degrees all the way around, okay? The shape of this, okay, I don't know if you see it, but I kind of see a triangle, okay, but we're going to be fancy about it. We're going to call it trigonal, okay, and then there's going to be a couple different types of trigonals. This one's kind of flat like a pancake, okay? Can you see it's just kind of super flat, okay? And so we're going to use the term planar. So we're going to use both those words, trigonal for the triangle, and the word planar because it's flat like a pancake. We are going to have some trigonals that are actually lifted up, kind of like a pyramid, but this one indeed is super flat. It's trigonal planar, okay? And one thing you're going to find out is that if all of the domains in your picture are bonding domains, which means that there's an element on the other side, then the EDG and the MG are going to be the same. So the molecular geometry is also going to be trigonal planar. The shape that the atoms make up are going to be the same as the shape that the electrons make up because everything is bonding in this particular drawing. And you might be saying, well, what if they weren't all bonding? And that's a great question. So what I'm going to come in here is I'm going to change one of these domains to be a lone pair. Okay, now I want to go back and talk about how we counted electron domains. I want to remind you, this is no longer a bond. In fact, this is just trying to show the geometry a little bit. So what I have drawn up here and this mean the same thing. So if I just had two dots up here, that would be the same thing as this. The only way that this could be a bond is if there's another element on the other side of the line. So this is a bond because there's elements on both sides. This is a bond because there's elements on both sides. This is not a bond because there's not elements on both sides. All this is saying is there's just a lone pair. So remember, this and this mean exactly the same thing. So in this case, I have a total of 3 electron domains, 3 total electron domains. 2 of them are bonding domains, and 1 of them is what we're going to call a non-bonding domain, or simply a lone pair of electrons. Okay? So what type of shape is going to exist here? Well, as long as there's 3 electron domains, those electron domains are going to get as far apart from each other as possible, and the shape is still trigonal planar. However, the shape that the atoms make up is no longer going to be trigonal planar. So I'm going to erase that. Okay? So what shape is this? Well, the nice thing about these models is that I can unscrew one of these. This is like where the lone pair is, so that we can come in and focus in on just the atom. So we're talking kind of about the shape that these atoms make, the BAB. Okay? And this is no longer a straight line. Okay? So we can't call it linear, okay, with the 2 bonding domains. Since it's not a straight line, the scientists came up with a nice fancy word for this, and they call it bent. Okay? So this is a bent shape, B-E-N-T, bent. And then the other thing that you need to know about lone pair of electrons that's worth writing down in your notes is that a lone pair of electrons has greater repulsion than bonding domains. So if this thing is repelling more, what happens is that this angle gets squeezed. So I always make this sound going, ee, kind of like squeezing the angle. And it gets into my students' head, and they remember it because it's one of the things that people tend to forget. But it squeezes approximately 1.5 degrees. Now, I like to say approximately because it depends on the central atom and what the non-central atoms are and their electronegativities and their atomic structure. Okay? But in general, about 1.5 degrees is a decent approximation for how much this angle gets squeezed. So this is no longer going to be 120 degrees. it's going to be about 1.5 degrees less than that. So 1.5 degrees less than 120, I think we're okay by saying 118.5 degrees. If I added 1.5 degrees, I'd get back to my 120. Okay, so that's what happens when you have two domains that are bonding and one domain that is a lone pair, or what we call non-bonding. Well, let's jump up to 4 domains. Okay, so let me put my water bottle back on and say, hey, what would happen if I added another electron? Okay, and a lot of times my students will say, hey, if it comes in here at the bottom, okay, these two are going to lift up to make a plus sign, and it's going to be 90 degrees. I'm going to say, hold on, okay? Remember, we're supposed to be doing valence shell electron pair repulsion. We want these domains, these 4 domains, 1, 2, 3, and 4, to get as far away from each other as possible. And I think there's a better way where you can get angles that are greater than 90 than just coming up from the bottom. Okay, and the answer is, if you come in from the top this way or the bottom this way, you can kind of almost assume what's going to happen. Okay, these other 3 are going to be pushed down by the repulsion of these electrons. Okay, and right now it's 90, and if they push down, it's going to be greater than 90. Okay, and I got a model that shows this. Okay, all of these things, okay, these 3 have been pushed down a little bit because of the lone pair that's right here. And as you can see, this thing is like completely symmetrical. It doesn't matter which one's on top. Okay, and we get this kind of shape right here that looks something like this. Okay, and I'm going to try to line that up a perfect way. Like maybe, yeah, that looks pretty good. Okay, this guy's getting a little wonky here. Okay, the glue's running out. So, but this angle is about 109.5. Okay, now drawing this is a little bit challenging. So I'm going to erase some things that are up here. Let's get rid of this drawing, and we're going to talk about having 4 domains. And this time we're going to say, hey, all these domains are bonding. We have 0 lone pairs, okay, and we have a total of 4 domains. So when you add these 2 together, you get this, and you get this shape. Now I have this green card here to show kind of like the plane that the board is in. And as you can see, there's a couple atoms that are in the plane, and there's an atom coming out of the plane, and then you got an atom going into the plane. Okay, so the atoms that are in the plane are this B right here, the central atom A, okay, and if I have this lined up perfectly, okay, this atom on the left-hand side is also in the plane, and the ones that are coming out of the plane is this one, and now I'm going to have to use a wedge when I'm drawing this because it's coming out of the plane, and I'm going to use a dotted line for this one because it's going into the plane. So drawing this can be a little difficult when it's your first time drawing it. So let's go ahead and do this together. We got an A right here. This one's in the plane. The one on the left is in the plane, and it's down a little bit. And the A is in the plane. Now we got this guy right here. It's coming out of the plane. So I'm going to use a wedge to show that. And then we got this guy that's going into the plane, because remember, it's behind the green card. And it's going into the plane. But all 3 of these B's are below the A. All 3 of these B's are below the A that's right there. Okay, so this is our drawing. Okay, and the name of this shape is called tetrahedral. And we know the word tetra means 4. Okay, we got 4 domains. There's 4 faces, so maybe that helps you remember that this is tetrahedral. And since all of the domains are bonding, remember when they're all bonding, that the EDG and the MG are going to be identical. And this angle is greater than 90, okay, but not quite to 120, because 120 was 3 domains. So each domain that you add, you're going to lose a little bit of, the angle because they're getting closer together. I don't think this is one that you'd be able to come up with off the top of your head, so you have to memorize it. The bond angle in a tetrahedron shape, okay, is going to be 109.5 degrees, not Celsius, just 109.5 degrees, okay, as far as the bond angle. So each of these angles in the tetrahedron are exactly all the same because it doesn't matter which one's on top. This angle's 109.5, this angle's 109.5, this one's 109.5, this one's 109.5, because the shape here is symmetrical, okay? So this is 4 domains, okay, when all of them are bonding. So let's kind of do a what if, okay? Instead of 4 and 0, what if I came in and said, hey, 3 of them are bonding, but we have a lone pair or a non-bonding pair? As long as this totals 4, the electron shape is going to be tetrahedral, okay? But what's going to change is the molecular geometry and the bond angle, okay? So I'm going to pretend that the top B is a lone pair, okay? So right now, I have this kind of shape with just my atoms, and we need to come up with a shape for just these atoms. So I'm going to come over here, and I'm going to take off the top water bottle, okay, to talk about, well, what type of shape would all this be? Well, as you can see, we still have that triangle shape, so we're going to call it trigonal, but it's no longer trigonal where it's flat like a pancake. That was our last one. This one is raised up some, so it's going to be called trigonal pyramidal because it kind of makes a pyramid shape. So we're going to call that trigonal pyramidal. And this lone pair is going to squeeze the bond angle a little bit, okay, about 1.5 degrees. So instead of 109.5, we're going to be at about 108 degrees because this lone pair has greater repulsion than bonding pairs, and it squeezes the bond angle, okay, here, here, and here. Or in other words, here, here, and here, because this lone pair is pushing everything together. All right, well, let's go a step further, okay? Instead of 3 and 1, let's take off another B and put in another lone pair so we have 2 non-bonding instead of just 1, but we still are going to equal 4, so we're going to have an overall shape that looks like this. We're just going to replace another one of these B's with a lone pair. Now, the electron shape is still going to be tetrahedral because if there's 4 domains, you're going to get that tetrahedral shape, okay, and they're going to get as far away from each other as possible. However, since 2 of them are non-bonding, when we talk about molecular geometry, we're talking about the shape that just the atoms make up, because molecular geometry is the shape that the atoms make up. So I'm going to come in here, and I'm going to take off another water bottle, okay, and talk about this shape, okay? You've seen this before, okay? You saw this when we took one off of this one, we called it bent, okay? So this shape, again, is bent, but the bond angle is different than last time because it started out as a tetrahedron. It started out at 109.5, and if we had 2 lone pairs, we'd go down 1.5 degrees one time, and since we got 2 lone pairs, we're going to go down 1.5 degrees again, so that's going to leave us with an angle of approximately 106.5. Remember, these are all approximations, okay? So when you have 4 domains, okay, 2 bonding, 2 non-bonding, we get this shape, okay? And that shape's called bent, and it has an angle of approximately 106.5, okay? And that wraps up 4 domains. Now we still have 5 and 6, so hang on, because we want to be masters of all of the molecular geometry, okay? But if you have found this information helpful so far, please hit a like and subscribe so that this information can be shared with all the other students that are trying to understand valence shell electron pair repulsion theory in a straightforward fashion, okay? So we're going to change this up. We're going to go all the way to 5 domains. So if we have 5 domains, 5 are bonding, 5 are, 5 are bonding, 0 non-bonding. So let me put this back together and talk about, well, what would happen instead of having 4 domains, we wanted 5, okay? Well, can you imagine what would happen if I came in and put the water bottle right here? Hopefully you'd say that this one, and this one behind me, okay, that they would all kind of like pop up, okay? And that's exactly what happens. And I have a model for that, okay? So if you look at this one, everything is kind of popped up. I have 5 domains, 1, 2, 3, 4, and 5, okay? However, 5 domains is very special because as I rotate it, you find out that it's not symmetrical. It doesn't look exactly the same as it did before when I rotate this around, okay? So because it's not perfectly symmetrical, okay, we're going to have positions. Where my hands are right now, we're going to call those axial positions, like it's spinning on an axis, okay? And if you think about the Earth, the equator would be going around right here where the other 3 water bottles are. So we're going to call these positions equatorial. So once again, axial when it's spinning on the axis, and equatorial for the other 3, okay? So how do we go about drawing this? Okay, well, same thing that I did before. Think about it. How many atoms do you see that are in this plane of what I'm using the green note card to kind of represent? Well, the atoms that I see in the plane are the ones that are on the top, the central atom, and the atom on the bottom. And then on the other side, it's still in that plane. So I'm going to use a dash for this one, a dash for this one, and a dash for this one. But I can't use a dash for this one because it's coming out of the plane. I'm going to use a wedge. And this one that's going into the plane, I'm going to use a dotted line. So let's take a look as to how I would draw 5 domains. So a dash going up, a dash going down, and a dash on the left-hand side because all of those things are in the same plane. On the other side, I'm going to use a wedge and a dotted line. So on the other side, I'm going to use a wedge and a dotted line. I'm trying to show this as kind of a triangle for the equatorial position. So remember, the one on the top and the one on the bottom, those are called axial positions, okay, and these 3 over here are going to be called equatorial positions, okay? So that's really important for us to kind of understand. Now, the shape of this, okay, if you see kind of like this triangle right here, okay, there's actually going to be a pyramid on the top and a pyramid on the bottom. So we're going to call this trigonal for the triangle, but a pyramid on the top, pyramid on the bottom, we're going to call that bipyramidal. So trigonal, bipyramidal. And since everything is bonding, it's going to have the same name, trigonal, bipyramidal. Just getting all types of fancy here, okay? Now, when it comes to bond angles, there's different angles because we got these different positions. If we're talking about axial to axial, that's going to be 180. If we're going equatorial to equatorial, that's going to be 120 because really that's kind of like trigonal planar still. So really this is like trigonal planar and linear put together at the same time, okay? But equatorial to equatorial, so I'm going to do EQ to EQ is going to be 120, okay? And then axial to equatorial, okay? Those are all going to be 90. Axial to equatorial is going to be 90. All right, okay? So once we have this, everything else becomes a what if, okay? Like what if we had a non-bonding domain? And if we had a non-bonding domain, one of these are going to be a lone pair, one of these B's. When it comes to 5 domains, where you place them is going to be important, okay? So whenever you add lone electrons, okay, they're going to go into the equatorial position, okay? So I'm going to come in here, and I'm going to make this an equatorial position. All 3 of these are equatorial positions, so it didn't matter which of these 3 I picked, but one of them is going to be a lone pair if we have one that's non-bonding and then everything else being bonding. How does that change things? Okay, it changes the name of the molecular geometry because I removed this atom. And remember, molecular geometry is the shape of the atoms. As far as the electron domain geometry, it's the same because we still have 5 electron domains. We just have a lone pair here instead of a bonding domain. So there's still 5 domains. You're still going to have trigonal bipyramidal. So I'm going to take off, we took it off the wedge, so I'm going to come in here and take it off the wedge, and we're going to talk about the shape that this guy makes. And as you can see, it falls over, okay, which is a good thing because I could hold this up, but it's easier to see the shape when it falls down, okay. If you look here, it looks like a seesaw, okay, and believe it or not, that indeed is the name of this shape. It's called seesaw. What does this lone pair do to all the bond angles? They get decreased by about 1.5 degrees. So this one's going to go down 1.5 degrees. So instead of 180, how about 178.5? Instead of 120, how do you feel about 118.5? Instead of 90, how about 88.5, right? Just check my math here, okay, because doing this all on the fly here, okay? And remember, these are all approximate, okay? Don't hold me very tight to them, okay? So that's what we have when we have 4 bonding and 1 non-bonding. So the next what if is, instead of 4 and 1, what about 3 and 2, okay? So we're going to come in here, and we're going to do 3 and 2. And what we learned from the last one is when you put electrons on, or the lone pair on, and you replace it with a B, it has to be in the equatorial position. So this is an equatorial position. So I'm going to do that for this one. Okay, so that would be the dotted line. So I'm going to take this guy off, okay, and we're going to talk about what is this shape. Okay, well, if I just turn it, it's really easy to see a T, okay, as in Tom Hoeffel, okay. And this is actually called T-shaped, okay. So when there are 2 non-bonding domains, okay, the shape is now going to change to T-shaped. And we're going to go down by 1.5 degrees again, okay. So instead of 178.5, that's going to be 177. Instead of 120 to 118.5, it's now going to be 117. And then, of course, this is going to be around 87. Remember, these are approximations, okay? And that's how we handle 3 and 2, okay? So a lot of vocabulary, okay? And as a chemistry student, you got to come back and, work on that vocabulary. The next video that I'm going to do is going to be a quick synopsis or review of all the different shapes that we're covering today in detail, okay? So the next one is going to be 2 and 3. What happens if I add another lone pair? Remember, it has to come from the equatorial positions, okay? So I'm going to place it right here, and I'm going to come in, and I'm going to take off the last one, okay? This is the equatorial position. It's the last one I need to take off. And what shape do I have? I get linear again. I get the straight line, okay, with a bond angle of exactly 180. So these 3 electron domains that are non-bonding, there's symmetry there, and I'm not less than 180. I'll get back to 180. So let's kind of write all that information down. So let's erase all of this, okay, and we get linear. And to be quite honest with you, the only thing that exists here is axial to axial. We get back to 180. If fact, in the last problem, there probably wasn't an equatorial to equatorial, so I probably should have put that in there. Okay, but we get 180 for axial to axial. And this happens when you have 5 domains, 3 of them non-bonding, but 2 of them bonding. You get this straight line or linear shape. Okay, last one. Okay, 6 domains. Okay, let's go back to 6 domains. This is where it ends when there are 6 and 0. So let me put my water bottles back on. Let me load up. And let's talk about if we get one more domain, and that's up to 6. Okay, so what do you think is going to happen if I add one more domain? Well, if it comes in here like this, these two are going to become kind of like a straight line. Okay, and I have a water bottle that shows this. Okay, you'd get something that looks like this. This has 6 domains, right? Okay, one on the top, one on the bottom. Okay, one coming out at you, one coming away from you on the left and the right. And this thing is symmetrical again. So I know you might want to call these axial, but they're not because it's symmetrical. So when you have 6 domains, everything kind of looks the same. Okay, it's perfectly symmetrical. And we got to be able to draw this. So let's kind of erase all of this. And we're on to our last molecule, okay, which is 6 domains. And this is how the note card is, okay. So how many atoms are in the plane? The top one, the central atom, and the bottom one, okay. On this right-hand side, we have a wedge and a dotted line. And the same thing is true on the left-hand side. We got a wedge and a dotted line. So let's kind of draw that. Straight going up and down. Wedge and dotted line on both sides. And what I'm trying to show here is kind of a square, because when you look at this, it kind of makes a square. I don't know if you guys can see that. A square going around the perimeter there, okay? So this thing has 8 faces. There's a face here, a face here, a face here, a face here for 4. And then same thing on the bottom. There's 8 faces. So we call this thing octahedral. Since everything is bonding, it has the same molecular geometry as the electron domain geometry, and it's a 90-degree angle, okay? So octahedral is our base shape when we have 6 electron domains, okay? Now, when we add lone pairs here, because of the symmetry, it doesn't matter which one you pick it from. But if you want to match most textbooks, okay, or the things that you might see on the internet, it's typically coming off of the bottom, okay? So if we add a lone pair here, and this changed to 5 bonding and 1 non-bonding, 5 bonding and 1 non-bonding, this molecular geometry is going to change because it's no longer octahedral, and it's going to have a particular shape. So let's take a water bottle off and talk about the shape, okay? It has a square bottom, okay? And it's making a pyramid shape. So square bottom in a pyramid shape, we're going to call that square pyramidal. Remember, when we had trigonal, there was one that was flat like a pancake, and that was planar, and the other one that was lifted up, and that was pyramidal. We're going to find that the same thing is going to be true for square. We have some squares that are pyramidal, and we have some squares that are planar. So we have to incorporate both words. This is the square that makes the pyramid, so we call it square pyramidal. What does this lone pair of electrons do on the bottom? It lifts everything up and it squeezes the bond angle by 1.5 degrees. So it's probably going to be around, and let's see, I think I did my math wrong there. There we go. It's going to be right around 88.5 degrees as an angle, okay? And that's what happens when you have 1 lone pair. Well, what happens if we do 2 lone pairs? Still 6 domains, just 2 that are going to be non-bonding. Well, if you have a non-bonding pair on the bottom, if another one comes in, it's going to go on the opposite side. Okay, so if we have total of 6 domains, 4 bonding, 2 non-bonding, but if there's 6 electron domains there, the electron shape is going to be octahedral, but the molecular geometry is not. Okay, so we're going to come over here. We're going to take off a water bottle, and we're going to have this shape. And now we got the square that's kind of like flat like a pancake. So we're going to call this square square planar. And because this electron domain and this electron domain levels everything out, it initially was squeezed, but the other electron domain puts it back down, so we're now back to 90 degrees. Okay, so I know that was a lot of information to process in one video. Okay, I'm gonna make another video where we just review all those shapes. Okay, so this video is kind of like first time learning of valence shell electron pair repulsion theory, trying to explain how and the why the shapes occur. The next video is going to be just a quick reference video so that you can study from, so that you can memorize all those different names, because there is a ton of vocabulary with valence shell electron pair repulsion theory, and that's where most of the students kind of like make mistakes on quizzes and tests. So please, if you don't understand how or why these shapes are formed, please watch this video again. But right before you study, watch the quick reference video that's going to be called Valence Shell Electron Pair Repulsion Theory Review. Okay, I'm going to have it listed as a review, and I think that'll help you like right before you take your next test or your next quiz that has this topic on the test or quiz. So once again, if you found this information to be straightforward and you like the how it's done and the format that it's done in, please like and subscribe and share to your friends.